What is the dimension of a vector space? We gave a few clues in the previous lesson. Let's now define it formally. So here's the definition of a basis. We already know what a basis is. It's a set of linearly independent vectors that's also a spanning set for the entire space. Okay, so that's a basis. And we've seen in examples that there could be many bases to the same space. Okay, so here's first definition. A vector space that has a finite basis. A finite basis means that it has some basis with only finitely many elements, is called a finite dimensional vector space. Okay, so I'm defining what it means to be finite dimensional before I define the dimension. Okay, so if you take a vector space, for example, R3, it has a finite basis. We saw in an example, we even saw two finite bases for R3. Then it's called a finite dimensional vector space. Okay? And we still haven't defined, wait, I know what you're going to ask. Wait, the answer is coming up. Wait. In this course, we are only going to be looking at, throughout the entire course, at finite dimensional vector spaces. All the theorems that we're going to state should actually start with the words, let V be a finite dimensional vector space. But since I'm saying it right now loud and clear, I probably am going to forget to start all the theorems with the words, let V be a finite dimensional vector space. Okay? So everything in this course is going to relate to finite dimensional vector spaces, except for a few examples that I'm going to give in a minute of vector spaces that are not finite dimensional, so you see that there are such things, and in fact you know them. I'm not going to invent anything that's new to you. Okay? So a finite dimensional vector space if it has some finite basis. Good? Okay. Theorem, and this theorem is a deep theorem. It's not a trivial theorem. In fact, it relies on, well, the theorem itself is easy to prove if you take for granted a deep lemma, a deep theorem that it's based on. And so right now I'm just going to quote it. We're going to discuss it a bit more later. Okay? The theorem is, let V, well, I am going to write it here, be a finite dimensional vector space. Finden wir's. Finite dimensional vector space. Good, everybody? Then, any two bases of V have the same number of vectors. Okay? So in the examples that we had for R3, we had two examples. Both were examples of bases for R3, both of which had three elements, right? This is not a coincidence. If one basis in R3 has three elements, there could be many bases, but all of them are going to have exactly three elements. Never two, never four. Okay? So this we're not proving now. We are going to discuss it a bit later. And now that we know this theorem, the definition, the number of elements in a basis for V, which is a finite dimensional vector space. So if V is a finite dimensional vector space, the number of elements in a basis does not depend on which basis you take. It's an invariant. That's what this theorem tells you. Okay, the number of elements, or the cardinality it's sometimes called. So this number of elements is called the dimension of V, and denoted by dim V. Good? So what's the dimension of R3? 3. Okay, clear? So now we know what the dimension of a vector space is for finite dimensional ones. Let's do a bunch of examples. So here's example number 1. The dimension of R3 equals 3. Why? Because in the previous clip, we saw a basis for R3. We even saw 2 of them, and they had precisely 3 elements. Good? Okay. Example 2. What's the dimension of F for any field 4? 4, right. Why? You should be able to justify. It's not just because the number 4 is sitting here. Why is it 4? Well, you have to go to the definition of the dimension. You have to say, okay, it's 4 because I can show you a basis for F4. F4 is n tuples with 4 entries, or not n tuples with 4 entries is ridiculous. It's 4 tuples with entries in F, right? What is a basis for this?
1, 0, 0, 0, 0, 1.
Exactly. The standard basis. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. That's a basis for F4. It has 4 elements, therefore the dimension is 4. Good? Clear? Okay. What is the dimension? What is the dimension of the vector space Rn of x? These are polynomials of degree less than or equal to n over the field R. What's the dimension? N plus 1. N plus 1. Why? Why? It's not just general knowledge. It's a very solid fact. We saw a basis for this vector space. The basis was the set of polynomials 1, x, x squared, x cubed, all the way to x to the n. Okay? We argued that it's indeed a basis, that they're linearly independent, and that they span everything. It wasn't that tricky, right? It was pretty much obvious. But it has n plus 1 elements. Good? Okay. 4. Now please don't jump with the answer. Think and raise your hand if you think you know it. So what's the dimension of matrices with m rows and n columns over, let's say, R? What's the dimension of the vector space of matrices with m rows and n columns? M by n matrices. What's the dimension? Yes?
I think it's m times n.
Very good. M times n. Why? Why?
Because you can, if you want to write it, the circle one.
We could translate it into an n tuple the size of m times n. We did this in the previous lesson.
Okay, so we need to show, you need to demonstrate a basis for this space that has m times n elements. That's what you need to do, right? So, for example, let's maybe do first a toy example where m is small and n is small. Okay, so e.g., let's look at m 2 by 3 over R. What is a basis? A basis is going to be the following matrices: 1, 0, 0, 0, 0, 0. Do you agree? 0, 1, 0, 0, 0, 0. And allow me to add dot, 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 each dot corresponding to a matrix. And finally, 0, 0, 0, 0, 0, 1. Do you see 6 matrices here? And do you see that any 2 by 3 matrix can be written as a linear combination of these? A general 2 by 3 matrix is A, B, C, D, E, F. It's A times this, plus B times this, plus C times this, and so on. Right? Does everybody see that? Okay. And they're linearly independent. How do you know they're linearly independent? For example, straighten them out as rows in a big 6 by 6 matrix, and you're going to get the identity matrix right away. No 0 rows. Good? So this is in fact, the standard basis for this space. Okay? And it can be generalized, and it has 6 elements, 2 times 3. Right? Do you see that? Okay. And this can be generalized. Maybe let's write it. This goes here and this goes here. So let's write it in general. In fact, I'm even going to change this R to a general field F. And the reason I want to write it more generally is because there's a bit of notation, of standard notation here, and I want to mention it. So this is an example. This is an example. In general, we write let's do this, just so I can write it more. So let's take V to be this, m by n matrices over the field F. And then the statement is that dim V equals mn. Okay? That's what we want to show. So let's take a basis for V. So a basis for V is usually denoted by Eij, Eij, where, so the set of these Eij's is a basis for V, where I have to tell you what do I mean by Eij, where Eij is a matrix that is all zeros, except a single one sitting in the ith row and jth column. That's Eij. And all the rest is zeros. Clear? Do you see that it's precisely this? So for m2 by 3 over R, this is E11, this is E12, this is E23. See that? Okay, so this is just notation. Do you agree? Okay, do you agree that this is a basis, just like here? Okay, I'm not going to write all the formal details, but it's exactly the same sort of arguments. Good? Okay. Okay. Here's another example. Questions about this? Is this clear?
I have a question about 1 actually. Well, it's a general question.
Okay, go ahead.
Earlier when we gave examples for bases, We used the example for R3, 1, 1, 0, 0, 1, 0, 1,
Right.
0, 1, 1. So could I take 1, 0, 0 and 0, 1, 1 and find that as a basis?
So
Why can't I do that?
okay, so the question is, we had a previous example in which we found a basis for R3 that had 3 elements, namely 1, 1, 0, 0, 1, 0, 1, and 0, 1, 1. Now you're asking maybe 2 of them would form a basis without the third one,
No,
right?
not 2 of them. I want to modify them a bit. I want to say that 1, 0, 0 and 0, 1, 1 would also be a basis, but
If you, are you taking just 2 elements?
I'm taking 2 different elements.
But you're asking if only 2 can form a basis? Well, first of all, the answer has to be no because of the theorem that I quoted, that any basis for R3 is going to have 3 elements. That's first of all. Now, second of all, you're asking, okay, why is my specific example? So you're asking, why isn't this 1, 0, 0 and this, 0, 1, 1 a basis for R3? The answer is it doesn't span R3. You can only get vectors of the form A, B, B. You would never get a vector of the form A, B, C, where the B and the C are different. So this set, they're indeed linearly independent, but they don't span all of R3. Good? Okay. Any more questions on these 4 examples? Everybody good? Okay. So here's example number 5. R of x. R of x is polynomials with one variable x over the field R, but with no limitation on the degree of the polynomial. Okay, so all the polynomials form a vector space, right? You can check all the axioms, they're all satisfied, right? But what can you say about the dimension of this?
Non-finite.
Right, it's not finite dimensional. Is not a finite dimensional vector space. Now, it seems obvious, right? You're saying, hey, clearly I can't find a finite number of polynomials that span every single polynomial, right? But the fact that you say clearly I can't find, well, maybe some alien can show up from a different planet and said, ha, you missed it. This is a 31,529 dimensional space. Here are the polynomials that you need to take that would span everything. Okay? So in order to prove that it's not a finite dimensional vector space, you have to somehow argue that there cannot be a finite basis for this space. Okay? And why can't there be, even if some very advanced life form arrives from a different planet, why is he necessarily wrong and there cannot be a finite basis for all the polynomials? Well, if there's a finite basis, then it has finitely many polynomials in it. One has the maximal degree. One of them has the maximal degree. Of a finite set, one has the maximal degree. Do you agree? And then you could never generate a polynomial with a higher degree than that by linear combinations of those polynomials, right? So if the highest degree is 1 million, and there are other polynomials, take linear combinations of them, you would never get a polynomial of degree greater than 1 million, right? Because a scalar multiple of a polynomial cannot raise its degree, and adding polynomials cannot raise the degree. Do you agree? Okay, so I'm not going to write all that down. Just tell me if you understood, if it's clear.
Would that be the actual proof of that?
Yeah, that would be, you have to write everything I just said without the stuff about the alien, and that would be the actual proof that R of x cannot have a finite basis. Okay? So if it were to have a finite basis, then there would be a maximal degree, and you cannot generate anything with a higher degree contradiction. It's not a basis. Good? Okay. Here's another example. So we had Rn of x. I just want to add Fn of x and maybe spell out. In fact, we did this. Okay, let's not write it. I just wanted to maybe generalize. Look here at this example. So do you agree that if I replace R by F, it would be the same thing, where the basis is just the set 1x, x squared, all the way to xn plus 1. Good? Okay. So questions about the dimension of a vector space. Is it clear what is the dimension of a vector space? Why it's well defined, okay? Even though it's the number of elements in a basis, and there could be more than one basis, that number is fixed. Okay, and that depends on a theorem that we mentioned but didn't prove. Okay, so what I want to do next is discuss some theorems regarding dimensions and bases. Okay, and of course they're going to relate to linear independence and spanning and all those properties, because that's how these notions were defined. Okay.